Imagine a cosmic object so bizarre, it does the impossible. It spits out matter and light instead of swallowing them. While black holes are the universe's ultimate prisons, trapping everything that crosses their event horizon, white holes are their mysterious twins, cosmic fountains that nothing can enter. For decades, scientists dismissed them as mathematical fantasies. But today, leading physicists are making a compelling case that white holes might be real, and they could solve some of the biggest mysteries in the universe. Welcome to the mind-bending world of white holes, where time runs backward, information escapes oblivion, and black holes might be gateways to new universes. The story of white holes begins in 1915, when Albert Einstein unveiled his general theory of relativity, a revolutionary framework showing that massive objects warp the fabric of space-time itself. When physicists applied Einstein's equations to predict black holes, they discovered something unexpected. The math had two solutions, not one. Theoretical physicist Neil deGrasse Tyson explains it brilliantly. If you ask, what's the square root of 9, you'd say 3. But -3 times -3 also equals 9. Both answers are equally valid. Similarly, Einstein's equations give us both black holes and white holes as legitimate mathematical solutions. In the early 1970s, as black hole mathematics matured, scientists realized these equations predicted white holes, regions of spacetime where everything only comes out, never goes in. But here's the catch. While we've photographed black holes and detected their gravitational waves, we've never observed a single white hole. This led most physicists to relegate white holes to the realm of science fiction. Until recently. Enter Italian physicist Carlo Rovelli, one of the pioneers of loop quantum gravity, a groundbreaking theory attempting to unify Einstein's relativity with quantum mechanics. Rovelli and his colleague Lee Smolin developed this framework in the late 1980s to address a fundamental problem. What happens at the center of a black hole? According to Einstein's equations, matter collapsing into a black hole forms a singularity, a point of infinite density where physics breaks down. But infinite values can't exist in physical reality. They're warning signs that our theories have hit their limits. Loop quantum gravity offers a radical solution. The theory proposes that space itself isn't infinitely divisible. It's made of incredibly tiny quanta, or grains, just like matter is made of atoms. There's a minimum size, 10 to the power of -35 meters, called the Planck length. When collapsing matter reaches this quantum scale, it simply can't get any smaller. Here's where it gets wild. Rovelli explains that spacetime generates a quantum repulsive force that opposes the collapse, causing matter to bounce back. During this quantum bounce, which lasts mere milliseconds from the black hole's perspective, the geometry of spacetime reverses. The black hole transforms into a white hole, occupies all the matter that fell in. But if black holes turn into white holes, why isn't our sky filled with exploding white holes? The answer lies in one of relativity's strangest features: time dilation. Massive objects don't just warp space, they warp time. Near a black hole's event horizon, time slows dramatically compared to the rest of the universe. Aurélien Barraud, a physicist at the Laboratory of Subatomic Physics and Cosmology in Grenoble, calculated that what seems like a few milliseconds inside the black hole could be several billion years for a distant observer. This means black holes formed at the beginning of the universe might only now be transitioning into white holes from our perspective. For stellar mass black holes, those several times the mass of our Sun, the transformation would take longer than the current age of the universe. We're essentially living before the white hole era has begun. But there's a twist. In 1974, Stephen Hawking discovered that black holes aren't completely black. They emit faint radiation due to quantum effects at the event horizon. This Hawking radiation causes black holes to slowly evaporate, losing mass over time. Rovelli and physicist Francesca Vidotto proposed in 2014 a remarkable scenario involving Planck stars, ultra-dense objects that form at the core of black holes. When a black hole evaporates down to a critical mass through Hawking radiation, it reaches Planck density, the ultimate limit of matter compression. At this point, quantum gravitational effects trigger the bounce, transforming the black hole into a white hole. Recent work by Rovelli and Vidotto suggests these Planck-scale remnants could be incredibly stable, surviving as tiny white holes with the mass of a microgram, but containing vast interiors. These objects might not explode violently, but instead persist as long-lived remnants. So how do we find white holes? Scientists have proposed several detection methods, and one of the most exciting involves gamma-ray bursts, the most energetic explosions in the universe. Barreau calculated that when a black hole transitions to a white hole, it might explode violently, releasing intense gamma-ray flashes. A 2012 paper suggested that the Big Bang itself might have been a massive white hole, and smaller white holes, dubbed small bangs, would eject matter in sudden pulses. Unlike black holes, which can be observed continuously, white holes would be momentary events. There's a specific class of gamma-ray bursts that appear in cosmic voids, empty regions of space, with no nearby supernovae to explain them. These mysterious bursts lack conventional explanations, making white holes a compelling candidate. The signature would be distinctive: gamma rays with a specific wavelength and an unusual redshift pattern. But Rovelli's most audacious claim might solve cosmology's greatest mystery: dark matter. This invisible substance makes up 27% of the universe's mass, but has never been directly detected. Loop quantum gravity predicts that after evaporating, some black holes transform into stable Planck mass white holes, objects weighing about a microgram each, but gravitationally significant. Rovelli argues that countless primordial black holes formed shortly after the Big Bang could have evolved into these tiny white hole remnants. Collectively, they might constitute a substantial fraction of dark matter. These objects would be nearly impossible to detect individually, but their cumulative gravitational effects could explain the mysterious extra gravity holding galaxies together. Rovelli's team is already working on hypersensitive detectors to hunt for these exotic remnants.